Hey folks, we'll talk about Le Chatelier's principle in relation to concentrations in this video. So what we said is equilibrium reactions are ones where the rate of the forward reaction and the reverse reaction are equal. Those things happen in what's called a closed system. And a closed system is one where there is no outside influence happening at all. So usually it would be something that we put a cap on a beaker and we let it just sit there. If it's an open system, that means that it's subject to change in the environment or subject to humans coming and changing the state of the reaction. So we're going to look at this reaction here today where we have Fe and SCN reacting to produce FeSCN with the 2+ charge. And the question that I have above is what would happen to this reaction if I added in more iron? And so what we're going to do throughout this process is we're going to use little arrows above the actual chemical symbols to indicate if their concentration or if their amount is changing. So if I am adding in more iron into this solution, what that means is that I'm increasing the overall amount of it that we have. We're going to assume this reaction had reached equilibrium, forward and reverse reaction rates were equal. Now I'm adding in more Fe. And the question is, how will this happen? Normally what I've done in the past is I've had students think about this as like a seesaw, where if a reaction is at equilibrium, we have a balanced seesaw. And we think of that middle part of the seesaw, the part that is on the ground, being like these equilibrium arrows. Well, if I add more Fe, what that's doing is, coincidentally, it's increasing the amount of weight that's present on one side of the reaction. And so if I was doing this here, what I would do is I would form a seesaw with my hands and lower one of the sides that is adding more weight, or we're going to look at an example where we take away more weight. So right now, this is what we're looking at here, is we have a seesaw that looks like this. Now, whenever we add or take away something from an equilibrium reaction, we're going to say that the reaction shifts in one direction. And so the way I taught my students is that whatever elbow is pointing up, that's which way the reaction will shift. So in this particular reaction, because I have this elbow up here, I'm going to shift the reaction this way. Or if we look at the seesaw that I drew present on the page, this reaction is going to shift to the right. In other words, the forward reaction will be happening at a faster rate until we can reach equilibrium. Now, if we think about that from a practical standpoint, if the rate of the forward reaction is happening more, it means that we are going to be producing more of this than we previously were. It means we're going to be producing more FeSCN 2+. But what it also means is that in order to produce more FeSCN, we see that we need some of this SCN. Now, I haven't added or changed anything about this SCN. Instead, all I've done is added in the Fe, the iron. And so in order to produce more FeSCN, I need to use up more of the present SCN that we have. And so this would be how those arrows would shift if we added in more Fe. You'd see that because we're adding in more Fe, the overall concentration of it will go up. Because we're shifting to the right or shifting towards the product side, or the product side is favored now, we are going to produce more of this FeSCN 2+. In order to do that, we need to actually lose or forfeit some of this SCN. And so that overall concentration of SCN would go down. And so this is how we'd see the overall changes in concentration with this particular reaction. Now, there's other cases that we can do as well. What would happen if we took out this FeSCN 2+? In the first video, I highlighted that potash is one of those resources in Saskatchewan where we take advantage of this reaction, where potash is one of the products and we take it out. Well, if we're taking out FeSCN, we know that its concentration will be going down. So if I draw my little seesaw, this is what it would look like if it were at equilibrium. Because we're taking some of it out, we're reducing the weight or the amount on the product side. And so we're going to see our seesaw look something like that, where if I'm doing my elbows here, we would see that this side would be heavier and the FeSCN side would be lower. And so if this side is going down and we see our little seesaw, we know again that we're going to have the same situation where we have this shifting to the right. If this is shifting to the right, it means the reaction, the forward reaction, is more favored. And so what needs to happen for that is that this Fe and this SCN both need to decrease. We need to react more of both of those, and so the overall concentration of them will go down in order to make up for the loss of FeSCN. So that's the second example here. The third example, what would happen if we took out SCN? So we're taking out or lowering the concentration of SCN. If we draw our little seesaw here, we're reducing the weight on this side, and so we're gonna have a seesaw that looks like this. Or if I were to do my elbows, we'd have a seesaw that now looks like this. And so because my elbow is pointing up on this side here, we can see that we're gonna have the reaction shifting in this direction. So this is the first example that we've talked about where we see a shift to the left. If we're shifting to the left, it means the reverse reaction is more favored, meaning we need to use more FeSCN to produce and make up for the loss of this SCN. By doing so, we're also going to be in turn producing more of this Fe3+ than we previously had. We haven't changed the concentration or taken away any Fe, but now we're increasing the rate and the frequency at which the reverse reaction happens. And as a result, we'll see an overall increase in that concentration of Fe. And so that is how concentrations work. We can do them by the arrows, but also the seesaw method as well to predict how these concentrations will change if we influence the equilibrium system in some way.